So my question for all of you is, what science do you plan to do with the first data preview with ComCam data and the first data preview with LSST cam data? What data products do you plan to use? And what do you plan on doing with those data products to get there? So I'm happy to serve as your trusty guide on your quest to figure out exactly what the data products contain, what the algorithms that produce them are, and other details about the data products over the next few days that I'm here. So I'm representing data management on Rubin construction. There's a handful of other data management people here as well. And from my point of view, the whole point of having talks is to give us fun stuff to talk about during the coffee breaks and lunches. So all of us really want to hear about the ideas you have and what you're worried about in terms of the algorithms and data products. And so when you see us, please feel free to ask questions of any of these data management folks. And I think I saw Mario Juric around here yesterday who can also answer questions about data management. Specifically, I coordinate for the Science Pipelines team, and I'm speaking on behalf of the entire Science Pipelines team. We are scientists first. We are here for the same exact reasons that you are. We are all excited about the discoveries and measurements that we'll make with LSST data. We're all members of a science collaboration, and you may not know, but every science collaboration has a data management liaison who you can ask questions of and voice your concerns to, and it serves as a way for data management to be able to keep up to date with advancements in science that we're expecting to do with LSST. So what the Science Pipelines team has in common is that we are all contributing to the LSST Rubin Observatory by writing the software that will take the raw pixels coming off the telescope and extract as much information as possible as we can from this multi-epoch data set. And this, you have to account for the effects of the instrument and the effects of the atmosphere to get the most accurate measurements possible. We're doing this by writing software. The software takes raw pixels and then processes it into both images and catalogs, two types of data products. We expect you to be able to do a lot of science with the catalogs. However, we know that you're going to come up with novel image processing algorithms that cannot be done with the catalogs alone. And this is why the images, the processed visit images, the difference images, and the coads are all first-class data products. You can use these to find your ultra diffuse galaxies, do your shift and stack algorithms to test your Planet 9 hypotheses. Now, there's no one pipeline that can complete all science goals. And so we strive to support as many science cases as possible in the science collaborations. We cannot include every single image processing algorithm in the data release pipelines. I know you would not be happy if data releases took 2 years. So if we have to make trade-offs, we promise that we will focus on the algorithms closer to the camera and the instrument, the parts that we know best. And this includes things like instrument signature removal and PSF models. Because we are committed to making it possible for you to use these data products, the coads and our PSF models, to do things like meta-calibration for shear estimation. So we plan on getting these data products to you in 2 ways, fast and slow. Fast is via the nightly alert stream, the prompt products. You'll see the acronym PP in the rest of this talk. This stands for prompt products. This is to support science that requires rapid follow-up. Slow are the annual data release products. This supports static sky science and statistical studies of variability. A misconception I hear all the time is that image differencing will only happen during nightly alert production, but this is not the case because calibrated light curves that have been globally photometrically calibrated to a constant 0 point is a data product of data release production. So you will get light curves as in data releases as well. You will access the data products via the Rubin Science platform, which we'll talk about a little bit when we talk about data preview 0. And I was planning on walking through all the data products that you see in the early data release scenario and how we include a little bit more data products with every single data preview. I will still offer that in the Q&A at the end, but in the interest of time, might as well move on. So the science pipelines, we have prototype pipelines in place, and they have been in use on real data sets. So first data set that we regularly analyze pipeline performance on is Oxtel. And Robert's going to tell you all about this, I think, on Thursday or tomorrow. This Oxtel is super useful for testing instrument signature removal because it has a real LSST cam chip, the same ones that you have on half of the LSST cam focal plane. And it was also the only telescope that was complete before the pandemic started. So we ended up using it for more integration than we were expecting to, since it's the only operating telescope on the mountain as of now. DCAM we use internally for testing the effects of DCR. It's useful because it does not have an atmospheric dispersion corrector, just like LSST won't. So we use this for seeing how differential chromatic refraction affects the performance of image differencing. We've done major data releases with both HSC and simulations. Simulations from DESC's DC2 run 2.2i, and this is the exact same data set that Dominique was telling you about yesterday and Bob mentioned this morning. Simulations are useful whenever you need a truth catalog measuring quantities like completeness and purity of your detection algorithms. It's also been really useful for guiding our intuition on the geometry of the camera and what happens to the algorithms when you're trying to make a coad of 1,000 visits. Hypersuprime cam, but it doesn't, so simulations are great for some things, but not everything. It doesn't have all the gory details like real data, like glints, reflected light, and really complex backgrounds. For that, we use Hypersuprime cam, which has been super useful because it goes really deep, as deeper than we expect from LSST. And this has helped us update our intuition on what happens when you try to process very deep data. Deblending gets more difficult, as you would expect, because at these depths, almost everything is in a blend. The other reason is that the HSC pipelines are the LSST science pipelines. And there's been no better feedback than real scientists in the HSC collaboration trying to write papers with our data products. So we've had 3 data releases, public data releases with HSC so far. And we have another one planned for next fall. The pipeline freeze for this has already happened at the end of May. And if you want to get a handle on how the pipelines are performing on real data, I recommend that you take a look at these data sets. We have a nice website, and if you go to available data and click on quality assurance plots, you can see very nice plots of how we're doing in terms of astrometric performance and photometric performance. This data release was done with a pipeline that's kind of old, and at the end, I will make sure that we go over everything that has been updated algorithmic-wise between 2020 and 2022. So this is useful because it uses the same algorithms and you get the same flags. And so you can try out how to get clean samples for your use case using the flags that we provide. Some caveats are that the column names are a little bit different than you'll see from DP 0.2 and from what we expect with Data Preview 1. There's no science platform available. And the survey strategy for the Subaru strategic program is not really conducive to difference imaging. It images this part of the sky on one night, this part of the sky the next night, this part of the sky the next night, and it doesn't go back to the same part of the sky over and over and over, except for the deep drilling fields. So it's possible that in the future we will run the difference imaging pipeline on the ultra deep field for HSC, but as of the previous data releases, we have not. So it does not include the difference imaging data products. Okay, so you notice that I mentioned it doesn't have a science platform. So it does, and different column names. So it doesn't really get you practice in interacting with the data products the same way that you would with the Rubin data products. And that is what the purpose of Data Preview 0 was. So Data Preview 0 was processed DC2 simulations. DP 0.1 used that same data set that Dominique was telling you about yesterday that was simulated by Desk and also processed through the same LSST science pipelines with a fall 2019 version. And then Data Preview 0.2 used the same simulated data set, but then used for reprocessing LSST science pipelines as of September 30th, 2021. So there's about a year and a half of updates to the pipelines that have occurred between those two data releases. And it's if you want to compare the effects of algorithms, it makes it particularly useful for that. Now, I've heard a lot of people say things like, oh, but Desk didn't simulate the objects that I study. I'm not going to learn anything from it. And let's be serious. If Desk did simulate your objects that you study, like, would they really have done it as well as you could have? And we probably would be having the same conversation about how they didn't use your models and you still can't write a paper with it. And I think that's inevitable whenever you have simulated data. You're not going to write papers with it, but that's not the point. The point is really to get used to how you're interacting with the data products, the column names, the flags, the science platform. And I know a lot of you are DP0 delegates and have been doing some really great work. I know like Vincenzo Pacheca has an epic community post having rediscovered that our plan for building templates in a very naive way of including all 5 years of visits in the templates is maybe not the best strategy. And that Supernova were linking into the coads, which was definitely something that we had expected to see, and was very happy to see some real data and examples of that. So thank you. So yeah, I realize that not everybody has time to practice interacting with the science platform now, and that's fine. So I will show you some screenshots. The science platform has 3 different modes. There's a portal which lets you filter on rows. So this lets you do cone searches and treat these as tables. There is also a hierarchical image viewer that lets you zoom in and zoom around the images. That video is not playing. The notebook aspect is very powerful. And the goal of this is to bring you and your code to the data and have it feel like you're working on your own machine. So you go here and you'll find a series of tutorials where you can learn how to interact with the butler, how to get data products from the butler. And you also have a terminal where you can pip install your own packages, git clone your own packages, and run your own software on the images and the catalogs. If you don't have access to the DP0 science platform, then you still have access to the schema. So if you go to the SDM, stands for Standard Data Model Schema browser, there's a list of all the tables that are available and all the column names that are available and descriptions for each of them. If you ever need to look up a table, a column name, I recommend that you go there. Okay, so I mentioned earlier that the algorithmic contents of each of these data releases has changed over the last few years. So the dates on this slide are the release dates, not the pipeline dates. The pipeline freeze dates for DP 0.1 and the HSC public data release 3 was roughly the same time. So in a second, I will explain what changed between DP 0.1 and DP 0.2. So if you see any differences and look into any differences, these are some potential possibilities for what caused the differences. And then between PDR3 and PDR4. So that first timestamp, February 2020, is pretty close to March 2020, which is when we had the algorithms workshop. This is a very great snapshot of where the status of the algorithms at March 2020 were. And the status has changed, of course, but the plans are all still current. So if you are curious what the plans are for background estimation, what the plans are for shear estimation, I highly recommend that you go and pick your favorite talk from this list. Okay, so major pipeline changes in the academic year 2020 to 2021. Primarily, we completely changed our middleware. And yeah, this was a huge undertaking, but has made things possible in the pipelines that were not possible for. So this naturally gave way to the data release production difference imaging pipeline, which was actually impossible to write with the limitations of the Gen 2 middleware. We also used Scarlet for co-ed measurement and sort of changed the definition of is primary. It's not that we changed the definition of it, it still means the same thing, but how it's computed has changed a little bit. We added satellite detection and masking during co-edition. So the coads are a little bit cleaner of satellites. We now measure galaxy colors using Gaussian aperture and PSF photometry, or HOP for short. This is our recommended column for galaxy colors to use for your PhotoZ estimates. There are survey property maps, which are now an output data product, and the transformation of the output catalogs to parquet tables in a standard data format is now native. So the column names between DP 0.2 and DP 0.1 have changed because for DP 0.1, Desk wrote their own afterburner converter to do the ingestion of the data products to a database. Okay, so differences between DP 0.3 and between PDR3 and PDR4 are everything that you saw on the previous slide, plus everything that happened in academic year 21 and 22. And this roughly, I gave a talk at the PCW about everything that we changed in the pipelines over the last year. So if you have any more questions about this, always happy to talk about what we've been up to. Okay, some highlights. Scarlet now fits within our compute budget. You might remember from the algorithms workshop that we were a little bit worried that it would take too long to run. Now, Fred Mullenkamp, the author of Scarlet, realized that Scarlet was more flexible than it needed to be. It can handle the case where you want to joint process multiple cameras with different pixel scales. It's meant for joint processing space-based data and ground-based data. For just the Rubin pipelines, you do not need that level of flexibility. So if you dial down the number of cameras that you have data for to 0, or sorry, to 1, where you have just 1 camera, then you get Scarlet Light. And this was because he was able, in that regime where you are only processing data from 1 camera, you can use analytic gradients instead of autograd. And this reduced the memory usage by an order of magnitude and reduced the runtime by a factor of 5 to 10. We are now using PSFs in the full field of view. This is a PSF estimation algorithm from the Dark Energy Survey, written by the same. So in the Q&A yesterday, we talked a little bit about how there's a lot of overlap in the actual people writing these algorithms between Rubin and DES and DESC. And this is one of those examples. We are also using the same stars to estimate the PSF in every repeated visit of the same part of the sky. So, okay, photometry and backgrounds. You asked me during the Q&A why I lumped these together. They're both enhanced in deep PDR4 by the fact that we now use Pan-STAR's pattern continuity algorithm, which ensures that background levels between amp boundaries are the same. So this removes amp to amp offsets that were causing the photometric residuals that we saw in PDR3. We improved outlier rejection in joint cal, which we use for astrometric calibration. This makes it scale better when you have 500 visits. Looking to the forward to the future, however, we are planning on using the astrometric calibration code from the Dark Energy Survey, which we call GB-DES. So that's been integrated with the stack, but it wasn't validated in time for the next PDR4. Okay. Well, okay, one point I wanted to make is that, so you may notice on the previous slide that we had a handful of algorithms from DES, for example, that we've been integrating into the science pipelines. And this is something that we are very prepared to do, have experience doing, and plan to do in the future. So we are committed to providing state-of-the-art algorithms. The state-of-the-art has evolved a lot over the last 10 years, and there's no reason to expect that it won't continue evolving over the next 10 years. So if you come up with a new image processing algorithm that is fast, robust, and enhances the data products and the scientific quality for all the scientific use cases in science collaborations, or at least does no harm, then it is something that we will seriously consider incorporating into the pipelines for future data releases. So I also wanted to say it's not too late to be a DP0 delegate. We're still taking, if you are an international data rights holder, get in touch with Melissa Graham if you would like an account, or if you would like an introduction, ask me during one of the breaks. I'm putting up a list of more resources for you to find out more info, and in effort of keeping the talk short and the Q&A portion long, I will put up a menu of stuff that I decided not to try to squeeze into the talk, but I'm happy to talk about now. So thank you. Thank you.
Explaining us how actually so expensive and important photons from source objects will be copying all down to the system and coming to our computers. So we have really interesting conversation on the Slack, and we also have some interesting mentions. So maybe we can start, for example, with the comments from the early career scientist who has already been mentioned during your Yusra talk. Vincenzo, would you like to comment something from your work, which already been mentioned by Yusra related to the
Okay. Well, I think what Yusra said is very important because it's very difficult to have a simulation which is complete enough. But I would encourage everyone to join DP0 and try to use those data, because trying to understand what problems are present and the entire pipeline can be useful. And it's better to understand that now than we'll have final data. So that's the only comment that I would like to add.
Thank you so much, Vincenzo. You have really interesting conversation, actually comment from Tom Wilson. Thank you, Tom, and we will read now. Quote, on the one hand, I only need to worry about what might be the default LSST product, the object yearly data release catalogs, but on the other hand, care perhaps more deeply than I should about the exact algorithms that go into how the pipeline makes those, more specifically in how mathematically astrometric position and corresponding photometric fluxes are computed. So please spare no gory details. And we have a comment that from Robert that you, Yusra, and Robert could give more than we, that you are both able to tell us more than we want to know. So please.
Okay, I didn't hear, is the question about how what the plans are for astrometric calibration, or how the object table is produced?
So maybe to answer both.
It seems to be that astrometric photometric centroid and
Hold on, Robert. Okay. Robert is the best person to talk about astrometric calibration.
the question seemed to be about how we actually centroid and calculate PSF fluxes. And I mean, I can answer those questions if you really want to know. It seems a little detailed here. You might be better to ask me afterwards. But the astrometric centroiding achieves the minimum variance bound given a Gaussian approximation to the PSF. And the photometry also achieves the MVB given an approximation to the PSF, plus an aperture correction to take into account the bias, but not the extra noise due to using a non-optimal PSF estimation. However, we're also using a compensated flux, which is basically estimating the flux of objects using a local sky subtractive. You can think about that for the 0-point calibration of the PSF fluxes, and also which will work correctly for point sources in moderately crowded fields. You get the wrong answers, of course, if you try to apply that to non-point sources. So there's all sorts of horrors in the galaxy photometry as well. And what's her name? Yusra, I nearly called her my wife. It also ends in A, which is a little confusing for me and her. But we're also measuring the galaxy fluxes in various different ways, both the overall fluxes in terms of model fits, but also these GAAP photometry, which is a PSF independent flux measurement for colors of galaxies. I think that's probably enough detail for the audience here, but I'm around all week.
Thank you.
To complement.
Sure. My slides disappeared. I guess one thing I will say is that for astrometric calibration, the the way we do astrometric calibration for the prompt products and the data release products are different. For prompt products, the goal is speed, and we plan on getting data products out within, or alerts out within 120 seconds. And so for prompt processing, we will basically rely on a reference catalog to do the astrometric fit. For data release production, we will do a simultaneous global fit. And so the WCS solutions for data releases are going to be much more accurate. And object tables right now, the way they're produced is we make coads and then deep coads to use for detection. We make coads for a handful of different reasons. Coads are useful for detection. They're useful for templates for difference imaging, and they're also this is new since 2013. They're also useful for measurement, and we're working on making coads that are suitable for measurement as well. We call these the small cell edge-free coads. So for detection, the objects, okay, and also some jargon. So for Rubin, sources are an individual observation of an object. An object is an aggregate of all the observations. It's something that has either been detected in a difference image or has been detected in a deep coad, or is a solar system object. So right now, objects are the union of all three of those.
Thanks, Yusra. Thanks, Robert, for these great comments. And we are coming back to the room. We have two questions. So we have two questions.
Yeah, thank you. Can you give us a comment or an update on processing the variable sources regarding determination of periods, amplitudes, and classification?
Oh, an update on what's happening in terms of the statistics on
processing of the variable sources. What you plan at the end to release?
Okay, so there's for the number of statistics that are being computed on light curves, there's a document that Eric Bellum wrote on this. I am forgetting the number of it, DMTN something something. Robert, if you can find that and post it in the chat, that would. Okay, there's a whole tech note to read on this. The plan is to include that in the DIA object table. So you take during prompt processing, you take an image, subtract the template off, get your detections in the difference image, and then associate those with the data DIA object table. If there's a matching DIA object, it just updates the ID to match that of that object. If it's not in that table, then you update the DIA object table and have a new entry in it. Then later during the day, you do pre-covery. This is and I actually can't actually advance the slides with this thing anymore. But then you have pre-covery, where for all the images taken in the last 30 days, we go back and do force photometry on those images. And so you can get light curve statistics out of that. And then of course, the data release production is going to produce super calibrated light curves that you can use if you need more precise statistics on your light curves.
Yeah, I was thinking more on processing of the light curves. I mean, determination of the periods and amplitudes. What do you plan to release? And if there are any updates? I know that there was a multi-band Lomskargel planned for the light curves and so on.
Yeah, so I can't off the top of my head enumerate everything in Eric Bellum's document. He put forth a proposal and I think put a post on community asking for input on it. And I will direct you to that community post and you can take a look there. So, but I don't think I know the answer to your question. Thanks.
Okay,
Bob.
We have a
I think part of that last question was, what do we plan to do with respect to characterization of variables? And I think the answer is we're not, that's for the community to do, right?
Well, we're not doing, I'm not sure I agree with that. So you can argue that the statistics that will be produced on each of the light curves are a object characterization. And in that sense, we are doing object characterization. I think, but we aren't doing, we're not going to pre-classify your objects. For the size pipelines, we're operating under the assumption that our expertise lies in pixel processing and that we don't have any special access to training catalogs or other observatory data that we can use for catalog only types of classifications. I'm sure you will be able to you have access to some training set and be able to write a machine learning classifier for the objects that you're interested in better than I can.
Okay, we are going to the third question from the room.
So thank you. I would pick your second bullet there. So can you mention the role of the different data facilities, including also from other international facilities that may be available?
Yeah, I can't, I can't actually go to those slides. So off the top of my head, I will just say that latest updates for the data facilities is that for the US data facility, we've completed the move from NCSA at Illinois to SLAC in California. And we are planning on having a hybrid model wherein we'll do the data processing at on-premises hardware, but we will continue to host the science platform and all the user services in the cloud, just like we're doing for Data Preview 0. So the cloud-based Data Preview 0 science platform, we plan on just leaving there. So 25% of the data release processing will happen in the US, all of the prompt processing. And then there's a French data facility at IN2P3, and they're going to be doing 50% of the data release processing. There's also the UK data facility, which will be doing 25% of the data processing on Iris.
Thank you, Yusra. That is the question. We have another question from.
Building on what Vincenzo was saying before, there were some problems discovered when looking at supernovae, but as far as I understand, most of the issue about light curves have been tested on transient sources. Now, in the AGN science collaboration, the issue of how to look at long-term light curve came out several times, and there is a problem there because we haven't been able to really test the performance because we need both to do the blending with the host galaxy and so possibly use difference imaging analysis, not force photometry. And that depends on the templates that you will choose. So as far as I know, so far, we've not been able to use either simulated data set because there are no AGN, nor the actual data because they don't cover an actual temporal span. So this is an issue that the science collaboration is stuck with trying to
work around that. But I was wondering if there will be a solution at some point that we can test our algorithms on.
Okay, and I know we had this conversation at the AGN Science Collaboration meeting earlier this summer. I'll just, for the sake of the audience, will say at least what we currently are doing as of DP 0.2, which is that the force source light curves are force photometry on both the direct images, the process visit images, and also the difference images. So the idea is that if you have an AGN in a host galaxy and you perform force photometry on the difference image, that the galaxy, the non-variable galaxy host will subtract off, and then you're left with only the variable part of the AGN at the center. And I know, yes, and we did discuss that this is insufficient for some cases. Okay, and I especially appreciate the idea that it's not, if the PSF on a coad is weighted by the same weights, the minimum variance for weighting, the PSF of a variable source is not necessarily the same as the PSF for a static source. And that is one thing that I especially appreciated from that conversation.
Oh, thank you, Yusra, for elaborating.
Did you want to say something? Up to him.
That is certainly true, but that's because it's a variable source. So you can get the light curve from the difference images. We'll do force photometry if you want the light curve. Your question is what the DC signal is, and you have to decide what you mean by that. You have enough information to extract that from the static sky. I think you even probably have enough information to extract that from the coad. You generate the custom PSF once you've got the difference imaging. It's pretty much a corner case to get the DC part of a variable light curve. And I think we have all the tools, but you'll have to use them yourselves. And the deblending for galaxy nuclear point sources is tough. And as we all know, getting low-level liner or something like that, light curve from the cores of galaxies is difficult because of astrometric problems in difference imaging. That is a generic problem in difference imaging. I don't know how well we're going to do, but I'm certainly aware of the issue.
Thank you, Robert. Okay. We are coming back to the virtual room, and there we also have some comments. The first comment from Nushkia Chamba: one of the things I found challenging when I was active in Stack Club, it was most active in 2020 and 2021, to engage with the Rubin science platforms and learn how to use them, was the timing issues. Since it is led by Greg and Alex in the USA, maybe we should think of having European-friendly time zones stack clubs. If this exists already, I do not know. Please tell me.